about how pressure, because I noticed as you were thinking of your explanations for all of these, a lot of us were getting a little bit stuck on these pressure differences and the pressure, what was causing that change in pressure inside your can. So on Friday, you started reading about pressure. Learned both about air pressure and atmospheric pressure. And so I want to quickly review that. So if you can take out your yellow papers, most of you have it out already. You read about air pressure. So take that one out.
Oh, shoot.
And I want us to talk about, first of all, you read a paragraph that explained what air pressure is and why our bodies don't feel it. And so I'd like to know if somebody could put their picture up here for us, if somebody will volunteer their picture to illustrate this.
I go.
Are you really, Colin?
Yeah, put it up there.
Okay, so let's look at his picture.
It's not correct.
See if Michael's picture is similar to your picture.
Yeah, pretty sad.
He has this guy here,
They're like twins.
and he says, small molecules are in the air pressure. We gain more air pressure than we lose. We cannot feel it. So can you tell me a little bit more about that? No?
That's all I know.
Okay, so what I see here is some arrows pushing down on this guy. What's causing that pressure on the
Gravity.
person here?
Gravity, air.
So there's air, and what's that air doing?
Pushing it.
Okay, so it's pushing on this
Yeah.
person. And so if we were going to show the molecules, how could we add molecules to Michael's picture here? So we could add dots surrounding the guy. And what did your reading say? What's one reason we can't really feel this pressure?
It's too small.
Because the air molecules are really small. It's not like you're putting a pen. It's like, because we learn pressure is force per area. So they're really small. The area that they're touching is really small. We don't feel those molecules. And then what's another reason? It said that it's kind of what he's trying to get at here. What did your reading tell you why we don't feel those molecules also? It says, in fact, at ordinary altitudes, we don't feel the gas molecules pushing on our bodies because gas molecules inside our bodies are also pushing out with the same force. So a good illustration of paragraph 1 would show gas molecules inside your body also pushing out. Okay. We're going to talk more about those differences in forces, but I need a volunteer for number 2, an illustration of atmospheric pressure. Who wants to show their picture? All right, so we have a picture here of atmospheric pressure. Alicia, can you tell us about your picture here?
It's the earth, and then the little dots are like all the air, the air, and then all around the earth is all pressing down.
Okay.
It's the atmosphere.
And where is there more, like when you, if we're going to look at your diagram here, where would there be more pressure or less pressure?
More pressure would be like more like ocean or sea level. Less pressure would be out towards, like on top of a mountain or something.
Okay, and why would that be?
Because it's higher.
Okay, and if it's higher, then what can you say about the air molecules?
It's not as heavy.
Okay, so if you're higher up in the, like on a mountain, you have less pressure on you because there's fewer molecules up there. So the more molecules, what can you say about the relationship between amount of molecules and pressure?
The more the molecules, the higher the pressure.
Okay, so if you have more molecules, you're going to have more pressure. And your reading also talked about like a fish under the ocean. If the deeper it goes in the ocean, it has more water pressing down on it, so that's more pressure. And then the last thing you read about was how a barometer works. So can I have somebody's drawing of a barometer here?
Mine is not good.
So here we have a picture of a barometer.
Number 2?
He drew it in number 2, but it's also, he was using it to show atmospheric pressure. But let's look at this picture of the barometer. we have this glass tube and a pan, and it's filled with mercury, liquid mercury. And it showed you, it talked about that the mercury could fall out of this tube into the glass pan, but then you read about why it doesn't. So somebody explain why this doesn't just all spill out of the glass pan. Colin, can you tell us using a picture here?
Because there's more pressure pushing on top of it than there is inside the glass tube.
Okay, and so where's the pressure coming from?
The air outside.
Okay, so he drew that here. This air is pushing down against the mercury. So he drew it here, pushing down. And if these arrows were less, what would you expect to see happen? If he drew these arrows smaller, what could you predict would happen to that mercury level?
It'll go up
Okay, why?
because there's no pressure bringing it down.
Okay, there would be less pressure here, so you'd expect this level to go up. And so that's how a barometer works. It measures how much air pressure is pushing down against this material. And so because it's a liquid, it can push it down and push it back up the tube. The more pressure, the more this would go up this way. So let's keep thinking about this. Vernon, pressure is a force per unit area. So it's how much force you're putting on something per the space that you're putting that force on. And we usually think of forces as a push or a pull. And when we're talking about these molecules, do you think molecules are better represented as doing a push or a pull?
I think both.
Why?
Cause you can add I don't know.
Okay.
I was hoping you would give me the answer.
Oh, okay. I heard somebody say push. Why do you think a molecule
That's right.
might be a better represented by saying it's doing a push rather than a pull?
Oh yeah, I think because it's like, are we talking about pressure, right?
Mhm.
So I think we force it. I said push because you can't pull a force. You know, like you can push something and force it, but you can't pull. Force
Okay.
it.
Well, if I do this,
That's true, but
am I putting force on something?
no, not really. You put
I'm putting force in this direction, right?
Yeah.
So I'm pulling it towards me. But those molecules that we picture floating, you know, like moving around, do they have any way to pull something?
No.
They do.
Okay, so
They're always just moving around.
okay, so they're moving around, and so I think it'll be best if we think of them as doing a push instead of a pull, because they don't really have a way to grab on and pull something. So we're going to be thinking of the push, the force as being a push, okay? And we could represent forces by arrows. And so when we're doing a large force, let's represent using a large arrow and a small force using a small arrow. And then the last thing I want to talk about quickly here is balance of forces. So I need 2 volunteers. Okay, Simon?
Go, Michael.
And
Come on.
Michael? Come on.
Aww.
No, like this.
We got a camera.
Bones are thick gravy.
So,
Let's see.
like this.
Oh, that's
I want you to stand
touch
side
each
by
other.
side so everyone can see you. Okay, so I want you guys to show me equal forces. So push against each other with equal force. Okay, does this look equal?
Yeah.
It does.
Okay, how could you tell that it's an equal force? What will we see if it's an
They're
equal
not
force?
moving.
Okay, so if they're not moving, we're going to see an equal force. Now I want one of you to do a large force and one of you to do a small force against each other.
They gotta fight for it.
It's like tug of war.
So what do you want me to do?
Okay, so right now, okay, so Vernon did a large force and Fabian had a smaller force. So
He's got the small one.
you guys,
Oh.
give him a hand. So here's Vernon. He's here, and here's Fabian. How could you
You're too into force right now.
find this little piece of scratch paper somewhere and draw forces to represent Fabian and a force to represent Vernon? How could you draw that?
How small you are
So you're going to use arrows, and then who's going to have a small arrow?
Vernon.
Okay. And the larger arrow will be Vernon. And how should I orient those arrows towards each other?
One pushing to the.
Which direction should they be facing?
Each other.
Okay, they're facing each other, so I have an arrow here and an arrow here. And this one was 5 and this one's Vernon. So how should I fix this picture?
Make one shorter. And
Just
then,
make one longer.
yeah.
So
Yeah,
which
make
one?
mine longer.
The one on the right.
Okay, good. All right, so that's how I want you to think about force arrows today when you're trying to describe what's happening. Okay, and so on your worksheet, the one you picked up on your way in, it's called a balancing act.
We got a lot of worksheets.
You do.
Very big.
You're going to visit 4 stations today. They're 1, 2, 3, and 4 with your group. And you are going to, can I borrow this one here? Do the following at each station. There's directions to follow. And then you're going to make careful observations about what happens. Especially focusing on the air or the gas in each station. And then, so you're going to observe what you see, and then I want you to do a diagram of your pressure, the pressure differences that are being created. So where is there more pressure, where is there less pressure, caused by all these air molecules that we know are all around us, or all the air molecules that are in the marshmallows or the balloon or the syringe, okay? So you're going to do observations and a diagram, and then you are going to answer whatever the questions are at the station, and they'll go here in this part of your worksheet. Does that make sense? Okay, so to practice, you can find more scratch paper. We're going to practice with this balloon. I'm just going to blow up a balloon here, okay? So as I blow up the balloon, I want you to observe what happens, and then we're going to draw a diagram, okay?
Blow it up literally?
Okay, so what do you observe? Tell somebody next to you what you observed happen as I blew up that balloon.
Air pressure.
Okay, so what happened? What are your observations?
Is that what we're right?
You apply pressure with your inner.
It got bigger.
Okay, the balloon got bigger.
Big words are hard to use.
You apply pressure.
Is that what we're on our paper?
Okay, so we're going to first talk about our observations. So what did you see happen?
It got bigger.
So the balloon got bigger. Could any other observations? What do you mean by bigger? Okay, so the balloon expanded.
Spam?
And you could draw a picture of it if you wanted. So you could have a balloon like a before and after.
Wow.
Okay? Now let's talk about the pressure. What's going on with the pressure?
There's less pressure inside of it.
And we want to talk about inside and outside. So let's start with our before picture here. Where is there pressure on this balloon?
Now it's all nothing but liquid.
Okay, so where's there pressure? And how could I represent that pressure? So arrows, and I'm going to draw some gas molecules out here. Arrow, arrow, pressure.
Pressure.
Okay. Now, is there anything inside the balloon that I could add?
There is maybe a little bit.
There's maybe a little bit of air, so I could put like a little...
Excuse me. You put some spin.
Okay, and now I'm going to blow up the balloon.
Wow.
And so now I have my large balloon here. And talk to somebody next to you. What should I add to my picture here?
Inside molecule pushing that inside pressure. Inside pressure.
An air going in and an air going this way around it.
Yeah, inside the balloon.
Okay, so this is my before. This is my after. So what should go inside my balloon?
Air molecules.
So now I have more, I'm adding air molecules inside my balloon.
Yeah.
And they're putting
pushing outward.
outward. Okay, and then what about outside the balloon?
Less.
Well, they're still there.
So what's still there?
The pressure from the outside.
Okay. So there's still some pressure from the outside, but what changed, do you think?
All the molecules.
So Tani thinks the bigger difference is maybe that there's more molecules inside. We added air to it. But let's talk about the outside because we know there's still pressure around this balloon, right? So let's add some arrows. We have our air molecules. They're pressing against it. So you're going to draw a step point around. But why isn't this balloon still expanding?
There's still the same pressure.
So there's still, what do you mean by the same pressure?
Same amount of force pushing on it that there was before.
But as there was before?
Same
Before
amount
there
on the
was
inside
air in it.
as there is on the outside.
Okay. So as I decrease the or if I am blowing up the balloon, it's expanding. So what's happening? Drika's telling us that this balloon is no longer expanding because the pressure inside and the pressure outside must still be, like, it must have balanced out. But as I'm blowing it up, I'm increasing that pressure on the inside. Because why, Tani? Why did I increase, how did I increase the pressure on the inside? And what did I do to the inside of the balloon? What did I change about this balloon as I inflated it? More molecules moving around inside. Okay, so it's kind of hard to describe each one because there's like a before, a middle, and an after, but I want you to do your best to explain what's happening to each one as you do the steps at the station and think about differences in pressure. Why would something expand? Why would something not expand? Why would it deflate?
Keep putting air.
No.
Or is this just put it over? Let me see,
Yeah,
Jim.
put it to right
The other
here.
one's not labeled.
Where you're close enough to where you're not gonna crush it. Bring her out.
Okay, Michael.
Like that? And then do it?
No, pull it. Put your finger over and pull it.
Okay, so what happened when you
Oh, that's cool.
And if you let go of your finger, just
Look, it got bigger.
Oh, what's it taste? Oh, weird. Look, guys, I have marshmallows.
lift towards us.
But what?
It like hurts the finger.
You gotta suck. It's gross.
Oh, you made it stay that way?
You're what's in that glass? You're
Okay, so
Try the same
what did you see?
with the rocks.
Try to fart.
So I'm gonna say, I don't know, pull a plunger.
Syringe.
Yeah, but this is the plunger.
You have like hella wrinkles. Nice and spongy and look.
Marshmallow expanded?
Expanding when it was pulled up.
And they get big.
So as I pull this out, so if I put my marshmallow in there.
Oh, I just. It hurts my hands.
Okay, so if I pull this out, what's happening to the pressure on that marshmallow?
Letting go so
Stop doing this.
So the marshmallow expands, and so does the pressure on the marshmallow.
we're out of here.
Weird.
So there's less.
You're being recorded, Doc. Oh, it like.
Does it get smaller? Ew, it tastes
It gets bigger. The balloon gets bigger. Let's just say that.
Alright, but I sucked it out. Okay. It's nasty.
And now I like, now.
Tastes like plastic and water.
So you, what's your
Just let it
evidence
come
of
out
the
really
pressure?
quick. Any day now.
So you saw the marshmallow
That's what I know.
expand because the pressure,
That's filthy.
Okay.
so there's less pressure.
There you go.
Hey man, dog, you look a little flinky.
And then, but what,
Watch this, watch
the
this.
amount of air change?
Watch it. Don't drop it,
So-
Peter. Oh, you dropped it.
Oh, no, I still
I
did
went
that.
in sideways.
I still
There's
did
water in there.
I just pull it back and I increase
If
the
you
space.
want to.
Why are we doing this?
That decreases the
Air.
Oh, we're just observing.
Okay, it fills with air a little bit, and then we put it in the cold water.
So that's the opposite of what I have right here, though. I have it pulled out. So I have more space. Why does that make less pressure?
That's the cut, huh?
So if I pull this out,
Right,
I increase the amount of space.
I know, me too.
Yeah, tell me that thunder, she sucked on my toes.
But why does that make
Suck on my toes.
Ah, take it off, take it off.
And then if Danny, you said if I put it in, then what happens?
Ow.
Yeah.
That sounds hella funny.
Okay, we're getting.
Hella hot.
No, because what? Because the pressure.
We're starting out with the same amount of air inside.
When you may switch whenever you're ready.
When we're pulling or pushing, it's still the same amount of air inside. That's why when we pull it out, it's just going to return back to the normal, the state that we...
First of all, you hold air outside of the
What?
and so
There's questions?
what's happening to our balloon?
Deflate.
Yeah, deflating.
Deflated after
Why did it deflate?
Because it turned back into water.
So the steam turned back into water.
Yes.
And so let's talk about pressures here.
Pressure.
What?
When it was heated up, there was more pressure pushing upon the balloon. And then there was nowhere to go, so it caused the balloon to inflate.
Okay.
And once we pulled it down, all the steam and pressure kind of went down back into the funnel.
So the pressure, so when you cooled it down, what happened to the pressure in the funnel?
It's not pushing onto the balloon on the inside.
At all?
I think there's still some, but not as much
Okay.
to where it could inflate.
And so why did it actually get smaller? Why would it maybe, why did it shrivel up? Is there any pressure in the room around us?
Yeah, there's always pressure around us.
Okay, so how could that have an effect on your balloon?
There's more pressure inside, outside, so it's pushing.
More pressure where?
On the outside, pushing in.
Okay.
Then, I mean, in the beginning it's normal, like it's equal. And then when we changed the temperature, it made more on the outside, which is why it deflated.
Okay, good. Does that make you think about your can crushing at all?
Yeah, it's like the same thing.
You can actually read that? I see that they
So how does that make you think of your can? Javier?
I know, Javier.
What do you think, how does this relate to the can crushing?
The can cushion. Because it deflates when the temperature goes down, so it turns back into liquid. And just instead of crushing, in this case, it just deflates.
Okay, and what's causing that deflation?
There's no more pressure like there used to be.
Okay.
It's not at boiling point, so
And how about the pressure around the can?
all around that.
Or around your balloon here?
I don't know, it's room temperature.
So why is there pressure on that balloon? Where is the pressure on that balloon coming from?
To go down.
We're just checking.
Outside.
Okay, so all this air
It's
pressure
cold,
around
yeah.
it? Okay.
It's not hot to put pressure against it.
Okay, so let's think about our example in the front of class today. Which one has more of a force?
When it had heat, it had more of the force, and then it turned back down. When there was no more heat, then it was the other way around.
So try to draw that using arrows. Show me the pressure. What are we doing to the air?
Getting rid of the air inside.
You're pushing it out.
Put the balloon in. There's no more air to go in when you try to squeeze it back, so the air goes in the balloon.
Okay, so air rushes into the balloon. That's why it expanded. And what happens to, so you have your balloon in here and I let go. What happens to the air that's between the balloon and the water bottle when I let go? So it expands, and so what does that do to the pressure inside, between the balloon and the
Pushes
bottle?
air into the balloon and it makes the bottle go back to its regular position. Or tries to.
Okay, and what happens to the air molecules that are in the bottle when I let go?
More away from the balloon.
Okay, why?
Because there's pressure going inside the balloon.
Okay, and what else is happening as I let go? What's happening, so I have these molecules. If I put this in here, if you want to squish it. Now she lets go, and we see that the balloon filled up with air. But what happened to the air that, we didn't change too much, but there was air in the bottle already, and she let go. What happened to that air in the bottle?
It's still in there.
Okay, so the air, amount of air is in there, is the same. Is anything different about between squishing it and letting go? What?
There's air in the balloon right now, but then
As you can
when
see,
we don't squish it, there's no air in the balloon.
Okay, how about the space in the bottle? Did the amount of space in the bottle change between when I pushed it and when I opened it?
Yeah.
Okay, and so how do you think that difference could affect the pressure inside the bottle. Why don't you guys keep talking about that, okay? And then also talk about number 1, balloon 1. As this balloon is getting smaller, why is this balloon decreasing in size?
Because like the air outside of it maybe is overpowering
Overpowering what?
the air inside of it.
Okay, and so if we're talking about those pushes, which one has a bigger push?
The air outside.
So I want you to try to draw that with some arrows.
Okay.
So why does the balloon expand then?
Because when pressure is sucked out of the flask,
Yeah.
there's more room for the balloon to expand.
Okay, because
there's pressure in there that's trying to like expand the balloon.
And the pressure sucked out.
So what do you mean by the pressure sucks out?
Because when you suck the air out,
So you suck air out, what does that do to the pressure inside the flask? 55.
It reduces, so the balloon like has more room to expand because there's pressure inside the balloon. It's trying to expand it, but it can't because there's pressure in it. So
because there's pressure in the flask pushing against it, but as you suck the air out of it, it's decreasing the air inside the flask, making more room for the balloon to expand.
Okay, and so because that balloon's able to expand, if you think back to our forces this morning, what happened to the force inside the flask compared to the force inside the balloon? Which one had a bigger force for that balloon to expand?
It doesn't have a needle in the end. It's just
So good. You want to show that. So I like how you showed me forces inside the balloon. Now I want you to show me the forces that the air molecules pushing against the balloon.